he was geared towards atom cooling and Rosenstein composites. And he carried out such a kind of preliminary experience in the early stage of atom cooling in France. He worked with the eminent scientists and eminent lab in Marseille, and then moved to Tunisia, where he has implemented such a kind of discipline in Tunisia. And also, Professor Tamimi is heavily involved in physics for the development work at UCAP, and also he is a fellow of a number of societies, the American Physical Society, among others. And he is one of the pillars of physics in the African continent. And within the years, of course, he moved towards quantum computing, as he will definitely share with us this. Quantum computing is a hot branch and a hot topic, which is really moving very fast. In fact, yesterday, Canada has implemented its quantum computing strategy, and the government of South Africa is intending also to embark in quantum computing strategy. And for that reason, in 2 weeks' time, I think, correctly, my son Mahmoud and Razia are in charge of that, how can I say, special series of lectures given by META on quantum computing. And this is a really fantastic opportunity for you to be introduced to quantum computing field. I am here like you. I will be learning. That is why I'm here personally, and I will learn at the same level as you. Quantum computing is related to cryptography, to security, cyber, hacking, and all of that. And Prof. Tamimi will be giving us another view, and hopefully all of us will be involved in this. We will embark in quantum computing, at least within our PhDs. At the end of our PhDs, we should be able to embrace quantum computing. Thank you, Prof. Tamimi, to you.
Thank you very much, Prof. Maza, for these kind words. economies and etc. discussion of the big issues of the world economy. And one of the topics discussed yesterday was about quantum technology and the new quantum divide between big countries who has already programs and strategies for quantum, and others like us and Africa who are left beyond. And one of the aims of these lectures I'm trying to give different places is to enhance the awareness of young fellows about the importance of embarking in quantum. Okay? Okay. Well, here just some acknowledgements about the origin of the material I'm using, as I'm teaching also for the master students at the University of Tunis the same courses. And I have had the opportunity to give also this kind of lectures on the occasion of the African School of Physics. Maybe some of you attended already the last edition, 2020, and the edition of this year, 2022, held last month here in South Africa. Okay, also I will use some graphics. I didn't do them myself, so I'm using those from IBM Qiskit website, which is a very nice platform. It's free, everyone can log in and be introduced to quantum computing. It's named Qiskit. A few words about the context. It is very we are lucky actually in the quantum community to have seen these brilliant physicists, Alain Aspect, John Clauser, and Anton Zeilinger receiving the Nobel Prize of Physics for the year 2022, specifically for their work on quantum entanglement, which is one of the basic cornerstones for the quantum computing and the quantum technology. So this is a citation of the Nobel Prize organization. The prize was awarded to these three physicists for experiments with entangled photons, as you can read here, establishing the violation of Bell inequalities and pioneering quantum information science. So it can seem a little bit weird to award the Nobel Prize for a kind of violation of some mathematical inequalities, but it's very deep actually, and this work is having a huge impact on technology, as we will see. The illustrations here are just kind of artistic drawing or painting of what could be the entanglement of two separated particles. I will come back to later. And just to give you a flavor of what is basic quantum circuit, as you can see here. Of course, when you see this kind of circuits for the very first time, in general, student does not understand what is exactly, but my hope is that at the end, by the end of these lectures, it will become very clear and we'll understand what is exactly and how, with this kind of circuits, we can create entanglement between particles, or at least simulate it. So, as I said just before starting the lecture, quantum computing is really trending, and here a paper from Quantum Insider from September last year, reviewing the strategies of the big companies in quantum computing and the quantum technologies, and you can see very familiar names like IBM, Intel, D-Wave, Google, and others. There are like 600 companies now embarking in the world in this field, and a lot of money is put on that. And with achievements maybe every month or every couple of months. As you can see here, an announcement from IBM dated on November 9th, 2022. Presenting their very new quantum processor, Osprey, with 433 qubits. So the qubit, I will come back later for details, but everyone can understand that in quantum computing, the qubit is the basic unit equivalent to the bit in classical computing. Okay, and the number of qubits is very important, and what these big companies are trying to do is to build up quantum computers with high and high number of qubits. It's very hard, so this is really an achievement. And what is important beyond this achievement, that it is part of a roadmap in the case of IBM, but this is just an example. All the other, or most of the other companies have the equivalent roadmaps. This milestone was already announced a few years ago. So you can see here, this scale the years from starting from 2019, and we are around here. And the Osprey quantum processor was announced 4 years ago as a part of the roadmap, and the people in IBM have kept their word, and they did it. And what is announced in the near future is the first quantum processor with more than 1,000 qubits, and then up to 4,000 qubits in a few years, Kookaburra and others. Okay, so of course, the power of quantum computers relies on the number, not only on the number of qubits, but the number of qubits is very important. And part of the tasks that we are expecting from quantum computing will be possible with this number of qubits, like 1,000 or more. Yeah, on the other side, it was not expected at the very beginning, but new applications are possible, like reverting things, and instead of using entanglement to construct quantum processors, now it was demonstrated by people from MIT. This is quite recent, in December 2022. How it is possible actually to use quantum computing to observe entanglement, and with some links to theoretical physics and so on. Okay, so this is a brief, briefly the context. Now we will go into the main part of the lecture. This is the outline. Few words about the general information theory, known as Shannon information theory. Then what is a qubit, the importance of the second quantum revolution, and I will conclude the first lecture with that. So during this series of lectures, I will use this graphic as a kind of map. So what you see here in the bottom is a quantum theory. Information theory, the classical information theory, because classical information theory is a very well established one, linked to statistical mechanics, the Shannon's theorems, and also to classical cryptography. So this is the bottom part. Then on the other side, at the high part, we find the quantum mechanics, the basic quantum mechanics, Hilbert space, Schrödinger equation, everyone knows about that. Also the entanglement, the Bell and EPR paradox and correlations, the importance of measurement, the coherence, all the quantum properties of matter. And in between, so joining both, you find here in the middle, the quantum computing, the quantum algorithms, etc. Okay? And on the side here, there is a connection between information theory and the quantum mechanics through quantum key distribution. This is quantum cryptography. So what we will do is to just to review some important aspects of classical information theory, basic quantum mechanics, and then move to the heart of the topic is quantum computing and the quantum cryptography. So information, the classical information theory developed by Claude Shannon is aimed to quantify, quantify not in the meaning of quantum mechanics, but to measure or to have an objective measurement of the information. How to say if that resource has more information than another one. So it was done very rigorously by Shannon, introducing in particular a key quantity, which is the entropy here, H. As you can see, the formula is a sum of pi log pi, where pi is the probability of the different events. Well, I do not have time here to go into details, but let's say that the idea behind this definition is that the events with high probability does not matter a lot, are not the most relevant for information. I mean, usual things are not really interesting. What is interesting is what happens very rarely from time to time when the probability is very low. So that's why you find here, because obviously the probability are mathematically are less than 1, so the logarithms are negative, so that's why you find here the minus sign in the front. Okay. So what Shannon did mostly is he analyzed the ability to send information through a communication channel. So the question was, I have some information to send through a channel. It can be like when you make a phone call or anything like that. Given some bandwidth, what would be the maximum rate of transmission? And is there any limit for that? So this is what was mainly the work of Shannon, who demonstrated mathematically, and this was very important, that even in a noisy channel is not a perfect channel, it's actually what you find in the reality with some noise, with some perturbation from the environment. So even in a noisy channel with a low bandwidth, you can essentially have error-free communication that you could achieve keeping the transmission rate within the channel's bandwidth and by using some redundancy for correcting errors. Of course, there are a lot of ideas behind that, but the main idea that it is possible to quantify very rigorously what quantity of information you can transmit through a channel. But not to make it very formal and very annoying, let's play a game here, okay? To make the lecture a little bit more interactive. The idea is the following. We convene that I will send a message to one of you through a perfect channel, which is a noiseless one, which means that the information that I send will not be altered. It will reach you exactly as I have sent it. But I want to keep it a little bit secret between us. So we are using a kind of code to encrypt that. And in this case, the code is very simple. I'm sending you a sentence like this, and the code is that I'm removing all the vowels. Okay? I send you all the letters except the vowels. And the game is that when you receive this message, you can reconstruct it. You reconstructed it only by adding the missing vowels. Okay? So this is the kind of message I'm sending, very simple sentence, and the game is that you try to guess what the original message is.
French School of Physics.
Yeah, go ahead. Say it again.
French School of Physics has interesting lectures.
African School of Physics.
Yeah.
Why French? So, but this is interesting. It means that even decrypting the code cannot be perfect. But it can be. But if you do it twice, you will reach the right answer, which is indeed the African School of Physics has interesting things. So you see, it is very easy. Now we can make it a little bit more complicated. If I send message like that, not exactly the same sentence because you already know the answer. Another one through a noisy channel. So the noisy channel is tricky because, well, of course we continue to use the same rule, no voids, okay? You will have to add the voids yourself. But now the channel is noisy, which means that not sure if the letters I've sent to you has not changed in the meantime. Okay? So I don't know, maybe this R was not an R actually, it was another letter. Okay? So it's a little bit hard. So can you try to guess? It's short, huh? So what would be the... So you receive this message from me, some noisy channel changing some letters. So we have to find the right letters and add the vowels to get the original message. Any guess?
Quantum computers are fun.
Quantum? Quantum computers are
Fun.
fun. Okay, you have at least the last one is good. Okay. R cannot be a good answer because you should have at least 4 letters in addition to vowels. But you said quantum, this is good. Good guess. Because we can actually imagine that the W here is actually Q, and with the missing vowels, you can make a quantum with this. So I take it, okay? Quantum is okay. Quantum is okay, and fun is okay. What about the others?
Harmonics.
Oh, this is too sophisticated. It's very high level. What I'm proposing is much more basic. And it's a word I used a few slides ago. So first step, you just add the vowels, okay? So you add the vowels, you have fun. But here again, the channel is noisy, so even the vowels can be changed, okay? So I put them in a different color, and the vowel can be changed to another vowel or another letter, not a vowel, like here. But anyway, I think with this it's much easier now for you. And obviously it is that quantum information theory is fun, and this is the good answer. Okay? So this is the kind of games we can play with this channel theory, which is very sophisticated, a lot of mathematics. But just to give you a flavor, because it's not at the heart of what I'm going to say today. But if you want to know more, you have this very nice review paper by Mark White. It's available on Archive. And as you will like the lectures here, you can if you like, you can see it for more details. Okay. So now let's go to let's go further in this lecture and say a few words about the computers we are using today, because quantum computing means new devices called quantum computers, but we already have computers like this laptop we are using. So what is the difference, and why should we, it is good for us to go to these new devices? Let's first start with what we already have enhanced, the computers we use every day. As you know, we process the information according to the rules of classical binary logic. So the hardware, the processors inside the computers, this is basic quantum, not quantum, but computer science basics. You find it in the textbooks. Still, the devices themselves, the processors, uses quantum or are based. their mechanisms are based on quantum mechanics, because a processor like those who are in inside my laptop or in the smart homes or whatever, of course they are, as you know very well, you are doing the material science, most of you are based on semiconductors, on transistors, etc. And these materials and these devices work according to the quantum mechanics, to the tunnel effect, to the wave particle duality, all the quantum mechanics. But still, we do not call them quantum computers, although they are based on quantum mechanics. So we will call classical computers, like computers like these, but it is good to know or to confirm for young students that they are also based on quantum mechanics. But what would be the difference with a quantum computer? The quantum computer is based on other properties, other quantum properties, which are not exploited in the classical computers, namely the entanglement. This is the key word. The entanglement and the superposition, of course, they are not exploited in classical computers, and they will be the key for the quantum computers. So, the purpose of quantum information theory is precisely that, to take advantage of these properties, namely entanglement, this is the key word, in order to perform tasks which are not possible to do with present computers. So what are the most known applications before going into their details? First, quantum computing, with the aim to implement a universal quantum computer with quantum algorithms. And the second main part is quantum cryptography for secure transmission of information. You have also quantum sensing as a third component. I will not speak about here in these lectures. So let's review together in this first lecture some elements of binary digits. As you know, every information, numbers, text, letters, images, videos, sound, anything is encoded using the binary system. Each elementary character has a specific binary code in the form of a sequence of zeros and ones called bits. Bits stands for, you know, certainly it stands for actually binary digits. A bit is a binary digit, so it's a very long word, so we compress it to just to say bit. And when it becomes quantum, it's a quantum binary digit condensed to qubit. Okay. Well, you certainly know how to code a binary. For instance, if I take any number, let's say 17, you can easily obtain the code like that. So the binary code is 1001. Just an example. What is interesting with that example is the number of bits. So to code the number 17, you need five bits. But what for any other number? And the good question is how many bits you need to encode a given number, not 17, but any other number. And of course, you know already the answer. You can also revert the question and say, for a given number of bits, what is the largest integer you can code? And of course, it is 2 to the power n, starting from 0 to 2 to the power n minus 2. So this is very well known. I'm starting really from the basics. So for instance, with the 3 bits, you can code the integer numbers going from 0 to 8 minus 1 to 7 with these binary codes from 001 to 111. So 3 bits is not very good because we are almost there. What we use in our everyday life is the decimal system. So 8 and 9 are missing. So we'd like to add them. For that, we have to add a 4th bit. And doing that, indeed, we can code integers from 0 to 9. So we have all what we need for the decimal system. But by the way, we have 6 more available possibilities not exploited in the decimal system, going from this code 1010 to 1111. So what people did, of course, they just used these available codes to define the hexadecimal system, where you add here the numbers A, B, C, D, E, F. And A, B, C, D, E, F are not letters. Of course, they are numbers. Their values are 10, 11, 12, 13, 14, and 15. Okay? So this is for numbers, very briefly. For letters or other characters you are using for any purpose, like typing a text or preparing this presentation or what else, you need a convention for the codes, and this is the ASCII coding system. This is the international one used. And it has been implemented everywhere in the world. This is what is used now in our computers. So based on 7-bit registers that are extended to 8 bits, called byte. The word byte also is important in computer science. Byte means, in fact, octet means 8. 8 is a word of 8 bits. Okay. So if you need the ASCII code for any number, you can find it easily. It can be for numbers, like 0, for instance. 0 in ASCII code is not 0, but it has some code here, as you can see here, in 7 bits coding, 0110000. So if you convert it in decimal, it would be 13, or even 48 in hexadecimal. Okay, the letters also, etc. I'm not going into details. You have an appendix here for interested people with details at the end of the presentation. I will not present it here today, but it is available on the file, so you can see it if you like. Now let's move to the classical operations. This is the aim of this part, just to see later on the equivalent when we move to quantum. This is the idea, starting with very simple examples. So let's take a register, so a word, or a register with 8 bits, so a byte, with some code, whatever it is. And the question is, what kind of operations we can do, what kind of calculations we can do at this very basic level. So of course, all we can do is just to switch any bit from a value to another, 0 to 1 or 1 to 0. So it is very, very simple actually. So either you do not anything, this is identity, 0 becomes 0 and 1 becomes 1, or stays 1, or the inversion, the kind of swapping, okay? So this is all you can do. So I can skip this is some history. Yes, so the numbering systems also, I will go fast on this. Maybe just to let you know, as we are in the African context, that of course we use decimal system every day, but there are many other number systems, and some of them are still used in some areas here in Africa, like in Niger, for instance, the quinary system based on even the names of the numbers. I don't know if some people come from this area. To say, for instance, 6 or 7 or 8, in the local language is said 5 plus 1 or 5 plus 2, etc. Okay. So here again you have an appendix. I'm not going into details. Okay. So the main idea Yes, and the main interest of this decimal system developed through the history of humankind is making the addition of two numbers very easy to do. So for instance, here I take very large numbers, arbitrary ones, and if I ask you to make this addition operation, you can try to guess how long, what time you need for doing this operation. Just to add these numbers with a pen and a sheet of paper. 1 minute, maybe less. So it's very easy. It doesn't matter if there are very large numbers, it's very easy to add two very large numbers. Okay? Thanks to this decimal system, or even binary, where the position matters. This is the main idea. However, if you want to multiply these numbers, that will then change the operation. How long it will take? You can try if you have time, not with these numbers, but you can take any couple of large numbers and try to do the calculation. You will be surprised how long it will take. It can be very, very long time, and actually, the problem was solved before computers by introducing the logarithm, but this is not the topic of today. Just to see how at the very basic level we implement the addition of two numbers. A very brief review in the binary classical system before moving to quantum. Okay? So this binary system, introduced first by Leibniz, takes the two basic ideas of the decimal systems. First, the importance of the position, so position matters. And the key point also is the carry rule for the addition operation. Everyone knows from primary school what the carry rule is. So if you add 7 plus 6 is 13, so it's 3, and you carry 1 to the next column. Very simple, but very important. How does it work with in the binary systems? As you have only two possibilities, 0 or 1, so the basic operation here, the table of truth, is that 0 plus 0 gives 0 with carry 0, 0 plus 1 or 1 plus 0 gives the same sum 1 and carry 0, and 1 plus 1 gives a sum 0 and carry 1. Of course, if you master this operation at this level, you can then, using a calculator or a computer, make very, very sophisticated calculations. But the basic idea is this one. And how to implement it in computer science? Simply by using these gates. You recognize if you have had in undergraduate studies some computer science, electronics. You recognize these gates, the XOR and gates. And the idea is that you have two entries here, 2 bits, which each one may be 0 or 1. And as the output, you have 1 bit for the sum and 1 other for the carry. So the table of truth of the circuit, you can check that, and you have an appendix at the end of the lecture for that, to check that it is exactly what I have presented before. So now, just to have a flavor, what would be the quantum circuit equivalent to this very simple, what we call half adder, just adding 2 bits. It looks like that. So this is the quantum circuit for a half adder. Once again, when you see it for the first time, you don't get the point. What is it? Is anyone used to this kind of schemes? Hamza? Someone else? Okay, so we will go into details. I will show you how it works exactly, but you can already already see, it seems complicated, but you already see that there are some Q certainly is kind of qubit instead of the bits. There are not only 2, but there are 4. C should be something classical. You have symbols here on one line or on 2 lines, and you have other symbols here. What does this mean? So we will come to that later on. But it is good to see where we are going to have an idea since this time. So I said that if you master this very simple operation, you can do much more sophisticated calculations. And in this graphic, you can see the evolution of the supercomputers with the huge capabilities of calculations. It's a bit small here, but let me help you. It goes from 2004 to almost a few years ago. The power or the evolution of the supercomputers in some place, a national lab in the US, where they host one of the most important, it's Oak Ridge actually, where they host one of the most powerful computers in the world. So you can see that here the capacities are increasing steadily, reaching an impressive number of operations per second. It's 2 by 10 to the power 17, and even more now. So it's really huge, but it's necessary to simulate the weather forecast and so on. And of course, this was possible because we are here in part because of the first microelectronics and nowadays nanotechnologies and nanoelectronics. So you can see here how the devices, for instance, here the storage, the data storage devices evolved through the years, going from this is ridiculous, 5 megabytes. You see the people here to have the scale. And now on your finger you can have more than 1 terabyte. It's really impressive. How was it possible? Thanks to the miniaturization and this chart or this graphic from a recent review as well shows what we call the Moore's law. The Moore's law is the evolution of the computer. Here it is shown in a different way. I like it. It shows during the years, we are here. It was published a couple of years ago, okay? So we are here, so we have a forecast for next year. What it is showing is the size in nanometers of the devices, let's say a processor, one processor. What is the size of one processor, okay? So since the beginning, the processors were invented in the early 70s. So 10,000 nanometers, it's basically 10 micrometers actually, so microelectronics. And then it is reducing down to like 3 nanometers. And at some point we are reaching a limit, the atomic level. So this was a very good period for the development of the electronics as we are living today, but we are at the end of it. We cannot go lower than 2 or maybe 1 nanometer. It is impossible. So we need a new technology. At the same time, well, we can say, okay, that's true. We cannot reduce anymore, but we can duplicate. We can use several many computers at the same time to do the calculation. And the question is, are today's computers enough for what we need? What would be your feeling about that? Do we really need a new technology? Or what we have enhanced is okay for our needs, everyday needs, or even research and development? Well, I don't know for you, but I think anyone would say, well, I'm not sure that using your own machine, at some point you said it's not good enough. But even if it is the case, you will change for another classical computer more powerful. But the need for really a new technology cannot be felt at our level, but more when you deal with more sophisticated problems like those evoked by Malik at the very beginning, like cryptography. Cryptography and how to encrypt messages in a secure way. So this is a big issue. Later. So I will give details about cryptography later, but just all I need now is to be aware that for encrypting messages for secure communications, the used algorithm can be threatened by quantum computers. So, starting from this idea, several companies around the world launched very ambitious projects to build the first efficient and reliable quantum computer. I cite some. I'm citing here some of them. Well, it's not that easy. As you know, you are certainly following in the news from time to time what is happening in this field. Some prototypes are already available. Even now you have a kind of desktop with 2 qubits computer working at room temperature. It's done by the Chinese. It costs like $8,000 and you can buy it. It's available, okay? But it is very, very, very basic. What is really interesting is the possibility to have a kind of universal quantum computer with at least 1,000 qubits or more. And as I said in the beginning, this was announced by companies like IBM. Well, D-Wave already has something like that, but this is very specific technology, not universal. So it is coming, and within the next few years, we will certainly hear about universal quantum computers available in the research and development institutions, including here. I am sure about that. One of the milestones that triggered all the field happened a few years ago in 2019, when people from Google, mainly, announced for the first time what is called quantum supremacy, or quantum advantage. Let's say quantum advantage. What is it? So we are talking about classical computers, we know quite well. Quantum computers, I didn't give the details, but you know that it is something that is in development, okay? And the question is there any task, any calculation, any problem that a classical computer cannot solve while a quantum computer can? This is the main question, okay? And if it happens, we will call that quantum supremacy or quantum advantage. So this goal was, people are trying to reach it for a long time, and it has been achieved a few years ago. On a specific task, people from Google, and followed by others later, have shown that for some problem, kind of sampling problem, the best classical supercomputer in the world, like the ones I have shown in the chart, takes like, say, thousands of years to solve it, so it is virtually impossible, while a quantum computer will require only like 3 minutes of calculations, which is really impressive. Okay. And other examples came later by the Chinese and other people showing this. Okay. So now back to after this brief introduction. I apologize because there are a lot of things that are not already clear, but I hope that with the coming lectures it will become more clear for you. Back to the charts. To move now, or to review another part of the bottom of this map, which is cryptography. Okay. What is the cryptography? The more used. What are the more used cryptography systems today? Some history about the 70s. We can skip that. What is important is that since 1978, these people with the initials RSA invented what is named the RSA asymmetric cryptography or protocol. This is the protocol which is used today by most of companies when you use your credit card to order something on the internet or make secure phone calls on WhatsApp or whatever. What is behind the scene, what you do not see, is an encryption based on this protocol. Okay. And the idea behind the RSA protocol is very simple actually. If you take two prime numbers, say 3 and 5, and you multiply them, you obtain 15. Okay? Even when you take two very large prime numbers, it is an easy operation to multiply them. Okay? The opposite operation is very hard to get. So if you tell you, guess what are the prime numbers when I give you the product, this is a very hard problem. If I say 15, in 2 seconds you say, okay, this is very easy. It is 3 and 5. If I give you a higher number, it takes some time. But if I give you a very large number, it is virtually impossible for you to obtain the two prime numbers. Or this is the key point in the coding RSA protocol. Okay. So some review about the prime numbers here, as I said, and okay, so this is basically what I was saying, so I can skip it. The point is, I'm not speaking here about 15 or any other small number which is a product of two prime numbers, but about numbers like this one, this beast. It starts here up to here. So this is a number called RSA 2048. Why? Because when you write it in binary digits, it has 2048 binary zeros and ones, okay? And in decimal system, it has 617 digits. Each line here is 50 numbers, 1, 2, 3, 4, 5, 12 plus this one, 617. And this number is the product of two prime numbers, P and Q. The question is, what are P and Q? You can spend your whole life looking for it, you will never find it. It is impossible. Only the people who did the operation on the other sides, so the RSA company, because they built up a company and they are selling their protocol. They know the answer, but no one other knows. And this is the key point. Why that? Because if you look at the what is called the complexity classes, factoring, the factoring problem into what is called non-polynomial class problem, NP problem, which means that the scaling of the number of operations with the number of bits is exponential, as you can see here, 2 to the power n over 2. While adding two numbers is very easy, we have seen that. Multiplying is a little bit more difficult, but not that difficult. Any calculator can do that. It's n squared. And then you have, so all these are polynomial, then you have no non-polynomial, even non-polynomial complex problem like the traveling salesman. This is another story. So, say factoring is very hard to do. Okay. And this is one of the limitations. I said, are we happy with our computers now? And the answer was yes, to some extent. But when you face this kind of problem, it's not okay. So this computer cannot factorize RSA 2048. Okay. The good news, I'm almost done for this first part. The good news is that, how long now? 20, almost 20 years ago, 1994, Peter Shor, this guy, invented an algorithm that says that if we have a good quantum computer with his algorithm, the Shor's algorithm, and implementing the Shor algorithm on this good quantum computer, it will be possible to crack the code and to factorize these big numbers. So imagine what happens to all the cybersecurity people. They are really scared about that. Not later than last month, a Chinese group published a paper. I have it on my laptop, I do not have it here. Maybe I will show you just the abstract in the second part of the lecture. It is on archive. They claim that it is possible to crack the RSA 2048 number with a quantum computer with only 372 qubits. 372, so less than 400. And I have shown you that IBM, they have already a quantum processor with 433, and more is coming. So it is becoming realistic. The possibility to crack this code is becoming very realistic, and it's a matter of a large debate and controversial debate these days. Okay. So without going into details here, we will do it tomorrow for the short algorithm. Okay. The Shor algorithm is very powerful, like numbers with 500 digits, not 600, only 500. It takes like 2 seconds. It's, I mean, in real time you can do it. Okay, and also some old estimations in 2012 with some resources, it should have taken like only 16 hours to crack RSA 2024. Okay. So that's it for this very first part, with not a lot of technicity, but just a brief review. And we will go into more details in the next ones. I'm almost on time. Thank you very much for this first part. And any questions, if you like, or maybe later, or feel free. I'm proposing to take a small break. I know it is quite hard to digest.
Thank you so much for this fantastic overview on quantum computing. I must admit, I always say that I'm a student. I learn so much, and what can I say? I find it really inspiring and worth of it. So please, thank you just for this first lecture. We could just have rest in the coffee, could have tea break. In 10 minutes we come back. Okay. And you have the possibility to interact in the tea room, please. I would like just to mention that I have had the chance to be taught by Professor Anna Aspe, at the Institute, and I have had a chance to be invited to the seminar in Vienna by Professor Anton Zeilinger, 2 of the 3 Nobel Prizes. I must say, they are just a fantastic scientist, and that's why, how can I say, whenever I hear about quantum mechanics and the strange behavior of matter and quantum mechanics, like in this case here, I mean, this called 2048, and we can spend our life to guess. This is fantastic. Thank you so much. Let's have a break, please, and come back. Please be sure to come back in time, in 10 minutes time. Thank you.
For quantum, so now we will go into quantum.
Yes.